Thank you for inviting me to give a talk today to your webinar. And I would like to discuss with you about twinning engineering in bulk metallic alloys. So it's strongly connected to nanostructuration of materials. So why strain hardening is relevant? The strain hardening is the capacity of a material to be hardened by plastic strain. So strain hardening controls the stability of plastic flow. In other words, the necking. So it's important for the forming operation. And it controls also the stretch field at crack tip in fracture mechanics. So we want an ideal material exhibiting a high YS, but sustaining strain hardening. Unfortunately, currently in the literature, you can see the effect of grain size refinement of the YS. So this is what you can see on the graph here in this style. So the refinement of the grain size in metal is a very efficient metallurgical solution to have ultra high strength materials, especially with iron. So the main benefit could be interesting for combination between strength and other induced properties as weldability, workability, or coatability due to the low alloy metallurgy. But there is a problem because the YS increases a lot, but the uniform elongation, so the strain hardening, drop dramatically to low level, and it is a strong limitation for the use of this kind of material. So the problem is we have to find ways to overcome the detrimental effect of microstructural refinement in single-phase alloys, especially for YS higher than 1 GPa. So in 2005, Lou and Al have shown something interesting. By electroplating copper, they obtain copper with a high density of twins, and the mechanical properties are strongly improved for the copper. So it seems that the behavior of nanostructured metallic alloy by high density of twin is very promising, but the use of an electrode deposition process is not consistent with production of massive bulk materials for structural application. So an alternative metallurgical has to be proposed. So at first, I want to show you an application of twip steel. So as you can see here, the strain hardening of twip steel is very impressive. It's a real breakthrough in the advanced high strength steel. So why the strain hardening is so high? Is that by deformation, the alloys twins, and as you can see here, when there is no twin, you have cell formation, as usually observed. But in case of twinning at room temperature, you have a nanostructuration of the material by a lot of twinning. And what we have shown in different papers is that the properties are controlled by the interspacing between twins. So the problem with twip steel is that despite the high strain hardening, the YS is too low for anti-intrusion application, for instance. So this picture is a key picture of my talk. it is a TEM macroscopy during the recrystallization of tube steel. And what is interesting to see is that you have a volume fraction of recrystallization material, but in non-recrystallized material, you see twin mechanically induced at room temperature, persisting at high temperature. So it seems that twins are stable at when you increase the temperature. So the idea is the following. We know that YS is controlled by the twin spacing. So it has been proposed to induce a high density of twins by rolling at room temperature and to recover the dislocation by keeping the twin by thermal treatment at the temperature lower than the twin stability. So the first results I can show you is that we have deformed by rolling. So you can have an example of the macrostructure obtained after 30% of pre-strain and recovery treatment. You see that all the twins are kept in the structure despite the thermal treatment. So you see the results for 50% of cold reduction. In the high receive condition, it is a low YS material with a high strain hardening. But in fact, if you deform the material at room temperature of 50% of cold reduction, you obtain this curve with no uniform elongation. But by thermal treatment, you recover the strain hardening more and more as a function of the cold reduction. So you can have a material with YS higher than 1 GPa with a uniform elongation of 15%. So it is a strong improvement. And we show here the results with different cold reduction. And you see especially that 30% is very interesting because you obtain a YS higher than 1200 MPa and the uniform elongation of about 20%. So this graph shows that the YS decreases just a little bit, but you recover the strain hardening after the recovery treatment. So to analyze these results, it's beneficial to draw the strain hardening as a function of flow stress. It is so-called the Cox-making plot. You see in black the curve for the adhesive material, and you see in red the results obtained after pre-strain and recovery treatment. So what is interesting to note is that for a given flow stress level, for instance, 1300% MPa, you have a strain hardening much more higher than in the adhesive condition. So this plot is useful to claim if you have improved the situation or not. So it is a summary chart showing the difference between pre-strain in diamond as a function of the evolution of uniform elongation as a function of ys without recovery treatment, so diamond here. And this is the result after recovery. So we escape from the banana curve, showing the usual decrease in uniform elongation as a function of ys. So when we saw the promising results of this metallurgical route applied to tweed steel, we have applied the route to austenitic stainless steel. It's a white market, of course, and it's current developed alloys. So we have worked on the 316 austenitic stainless steel for energy application. So we have applied 37% of rolling and a recovery treatment of 1 hour at 600 Celsius degree and followed by air cooling. So by ABSD map, STM map, you see that after the recovery treatment, all the twins induced mechanically during the rolling are kept in the structure. So the structure is very dense in a twin. And so it is a kind of nano-structuring materials because the interspacing distance is very low. So in red, you can see the adhesive condition of austenitic stainless steel. If you cold roll of without any recovery, you have no uniform elongation. But if you do the recovery treatment, removing dislocation but keeping the twin, the ys is higher than 1 GPa, and you recover strain hardening after the treatment. So let's go back to the Cox making plot. So the strain hardening is a function of post-stress. So you see that in green, that for a given flow stress, the strain hardening is much more higher than in adhesive condition. So it is the confirmation of improved combination between flow stress and strain hardening. So more recent application, we have applied this metallurgical route to high entropy alloys. So it is a contour alloys. So in high entropy alloys, you can see the stress strain curve at room temperature and at liquid nitrogen temperature. So the situation is a little bit different in this case because the twinning occurs at low temperature, not at room temperature. So what we have done, we have pre-strained at liquid nitrogen the high entropy alloy, and after we have recovered at 73 Kelvin to reduce the dislocation density but keeping the twin. So this is a SCM picture where we see the effect of recovery on the structure. So you have a shift on the left for the number of fraction of high angle boundaries. So we can see now the effect of the recovery after pre-strain a liquid nitrogen. So you see the as-if condition, and you see the curve after different pre-strain of 20, 35, and 50%. So after the recovery, if you superimpose the curve shifted by the amount of pre-strain, you see clearly that for a given pre-strain, the strain hardening is improved after pre-strain and recovery treatment. So you can summarize in the Cox-making plot I see as I show you here, and we have improved the properties of high entropy alloy applying this metallurgical route. So in conclusion, the balance between strain hardening and strength in nanostructured material is a key challenge for the future of this field. The advantages and limitations of grain size refinement have been highlighted. A promising metallurgical route exploiting the thermal stability of mechanical induced twins in austenitic steel and in high entropy alloys has been proposed and applied, and the result confirms the opportunity to get nanostructured alloy exhibiting high YS with a high strain hardening using a realistic metallurgical route by twinning engineering. Thank you for your attention, and I would like to acknowledge Dr. Scott from Canada, Dr. Barbier from France, Professor Young Sheop Kim and Dr. Moon from Korea, and Professor Yuri Estin from Australia. Thank you.